Hello and welcome back to Introduction to Number Theory. In this video, we start a series of lessons where we study the behavior of fractional part of n alpha, where n is an integer and alpha is a real number. But first, let me remind you of what fractional part is. Well, we start from an integer part of x, where x is a real number. We call the greatest integer number n such that x is greater or equal than n. So n is an integer, and at the same time x is somewhere between n and n plus 1. And x can be equal to n. So if x is an integer, then its integer part is equal to the number itself. And the fractional part of x is not simply x minus its integer part. So it is the small thing. We understand that it is always within same interval 0 to 1. It is a very small thing that makes x non-integer. Now let's talk about fractional part of m alpha. Well, in other moments we can use different notations. Well, m is an integer, or most of the things we will state about fractional part of an alpha will also hold for natural n, which means positive integer. And alpha is simply a real number, and there are two completely different situations where alpha is rational and where alpha is irrational. So let's state it over here that we'll have two completely different types of behavior: rational alpha and irrational alpha. And of course we will start from the most simple one, from rational alpha. So put alpha equal to p over q, where p is an integer and q is a positive integer, and p and q are mutually prime. Well, this is because every fraction can be simplified to an irreducible fraction. We understand that fractional part of m alpha can be now transformed into m alpha minus k, where k is the integer part of m alpha. And this is equal to mp minus kq over q. So we understand that the fractional part of m alpha is a fraction of the form integer over q, because, well, obviously this expression here is an integer. Thus, we can now state that fractional part of m alpha belongs to the set 0 over q, 1 over q, 2 over q, and so on, and we know that fractional part is always less than 1, so q minus 1 over q. Please be careful, this brackets here mean the fractional part, and these over here mean the set of values. Now we need to answer the question whether all these values can be reached. Start from the property of P and Q being mutually prime. We know that the greatest common divisor of two integers can be represented linearly using these integers. It's a theorem about linear representation of the GCD. So there exist, I'll say, a and b integer such that a p plus b q is equal to 1. This means that 1 can be represented in the form like here, something multiplied by p plus something multiplied by q. Well, of course, here we have minus, here we have plus, but we know that we're dealing with integers, so it doesn't matter whether we say plus or minus. By multiplying this equality, we can get an equality in which something multiplied by p, or some integer multiplied by p, plus q multiplied by some integer can give us actually an arbitrary integer s, since s is arbitrary, and a and b, we know that they exist and they are integers. So therefore, for every integer s, there exist, let's denote them s a and s b, also integer, such that s a multiplied by p plus s b multiplied by q is equal to s, where s a and s b, this is how we denoted these two multipliers. So we can obtain any integer by multiplying p and q by some other integers. Does this prove that the fractional part of m alpha actually runs through all these values? Well, yes, the answer is yes, and this is why we can state so. Indeed, let s be not just an arbitrary integer, but an arbitrary integer between 0 and q minus 1. And find the corresponding SA and SB so that SAP plus SBQ is equal to S. Then divide this equality by Q. So we have SAP over Q plus SB is equal to S over Q. And now we understand that if M is equal to SA, So this is our m. Then the fractional part of m multiplied by p over q. Well, this is m p over q. This is an integer, and this is something which is obviously less than 1 and greater or equal to 0. So the fractional part of this number here is equal to s over q, and this is what we wanted to obtain. So now we understand that for any number in this set, there is an integer m such that fractional part of m alpha is equal to this number, and at the same time, of course, integer fractional part of m alpha can only have such values.